Cognitive Psychology, Chapter 5, Attention. As we discussed in the last chapter, our sensory system takes in an enormous amount of information. For example, each eye has 100 million photoreceptors, each of which is sampling our environment many times a second. Our brains are ultimately of limited size. This is demonstrated by the need for the sulci and gyri, which are folded to be able to fit more neural tissue into our skull. This finite size ultimately reduces the amount of computing power that our brain has in order to process all of that information that comes in through our senses. Attention arrives because our brain must choose which information to process and which information to ignore. Ultimately, it is a physical limitation on the computing power that our brain has. This selection process, which we call attention, will be the topic of this chapter. Although it may seem as if we're able to process all of the information around us and simply apprehend the world, most of the information that is available to us through our senses is actually not processed. Indeed, we miss many things happening in our environment. This phenomenon can be observed in something called inattentional blindness. When people are not paying attention to some stimulus in the environment, even if it is entering their senses, they will often fail to perceive that it's taking place or occurring. This failure is not due to impairments in the sensory stimulus. Visual information can be entering our eyes and being transduced by our photoreceptors, but still never seen by us because of the limitation on processing. In this particular example, if you move your eyes back and forth, it can be very difficult to detect the change until you happen to focus your attention directly on the location where the change is happening across the two images. If you still don't see it, please look to the left of the Sphinx's head. Do you see it now? If you still don't see it, this bush on the right is not present on the left. A more typical way to demonstrate change blindness is in this kind of image that is flashed repeatedly. Do you see the change? If not, look under the wing of the airplane. You might notice that the jet engine is appearing and disappearing across views. If you pay close attention, you'll notice that there's a gray screen introduced in between the presentation of the two different images. This ensures that we don't see the change because of the instantaneous presence of the jet engine directly beneath the wing. If that gray screen was not there, the sudden presentation of a change would attract our attention. The need for attention has often been described as a bottleneck. In a bottle, a large amount of items would spill out too quickly into the cup. The neck, which is a narrowing of the bottle, ensures that only a small amount of items can come out at a given time. Similarly, in the case of our brain and our sensory system, the sensory system is taking in large amounts of information. There's a bottleneck simply because the processing power of our brain is much narrower. Therefore, there needs to be some process of selection to choose which of the items that are in the sensory system will ultimately be further processed. Attention is often described as a filter. Selective attention, when someone pays attention to one thing and not the other, is similar to a filter that only allows some items to pass through while others are neglected and left behind. Again, the sensory input would be the input to this attentional system. The filter would be attention itself, and then whatever made it through the filter of attention would go along for further processing. Selective attention can be demonstrated in a phenomenon known as the cocktail party effect. The cocktail party effect is something we're all familiar with. If we're in a noisy and crowded environment where lots of people are talking, such as this crowded bar, we may want to pay attention to the words and the conversation of a specific individual, and in some sense ignore the information from all the other individuals who are talking. This problem may seem simple, but is in fact extremely difficult, and that's because all of the sound from both the individual we're speaking to as well as other individuals is ultimately making its way into our ears and is being transduced by the sensory system in our ears. Our brain ultimately does not want to process all of that information, only a subset. Therefore, attention, and specifically selective attention, must be imposed in order to somehow select the information that we want to further process to understand the conversation we're having with one other individual and neglect to process the other information. An important tool for studying selective attention is the dichotic listening task, first introduced by a researcher named Cherry in 1953. In the dichotic listening task, the participant wears a pair of headphones and is presented with different information in each ear. The participant is instructed to attend to only one source of information. For example, in this case, the participant is told to listen to the information in his left ear and ignore the information in his right ear. In order to ensure that they are paying attention to that ear, they are usually asked to repeat the information that is presented in the intended. Overall, Cherry found that participants seem to be almost completely unaware of the content of the information that was presented in the unattended message, even though it was presented directly to their sensory system. However, participants typically are able to identify some significant physical change that's taking place in the unintended ear. For example, if the voice were suddenly to switch from male to female, or to grow very loud or very soft, participants might indicate that they notice this change. However, if asked what the content of the information, the meaning of the words that were delivered to the unattended ear, they typically would respond that they had no idea. What these early experiments demonstrate, and what selective attention in general demonstrates, is that attention means that not everything is processed equally. Information that we pay attention to, we remember, we understand the meaning of, and we are able to converse about. Unattended information, on the other hand, is clearly not given this privilege. The question then arises is how much does unattended information get processed? Does everything end at the sensory system, at the eyes or ears, and does that information get no further processing? For example, when a participant is listening to a dichotic listening task, the information presented to the unattended ear, what happens to that information? Is its meaning processed at all? Does it ever make it past the initial sensory stage? Two basic families of models have been presented to deal with this question. In early selection models, selective attention acts as a filter based on simple physical properties. For example, the pitch or the volume of the unattended message would be used in order to filter it, and no further processing takes place. Think again about the conversation in the cocktail party effect. The person you're speaking with has certain qualities to their voice. The information in their voice is coming from a certain location, which may be identified based on the fact that sound hits our two ears at slightly different times. This is how we're able to localize sound in the environment. These simple physical properties, while still requiring the brain in order to process them, still represent a very limited form of processing. For example, they don't include meaning. So the other conversations in the cocktail party effect that you're not paying attention to, according to early selection models, the meaning of those conversations would not be computed at all by your brain. Only the simple physical properties that are needed in order to decide whether to select or neglect the information would be processed. Because Broadbent's filter model is an early selection model, any information that does not make it through the filter is not processed in terms of its meaning. However, from the beginning, there have been challenges to the early selection models. For example, Moray, using a dichotic listening task, was able to show that some information does get through. For example, when participants' names were spoken through the unattended ear, they often noticed that their name had been spoken. Recall that according to early selection models, only the basic physical characteristics, such as pitch, volume, or location, of the unattended stimulus should ever be consciously perceived. The fact that people were perceiving their names and detecting it seems to challenge a very direct interpretation of the early selection models. Another challenge to the early selection model came from Gray and Wedderburn. In an interesting twist on the dichotic listening task, they presented a coherent story beginning with the words "Dear Aunt Jane" and then continuing on from there, such that it alternated between the two ears. So "dear" might be presented to the left ear, "aunt" might be presented to the right ear, and then back to the left ear for "Jane," and so on. In addition, they presented numbers in between each of those words to each ear. So in the left ear, one might hear "dear," then the number 7, then the word "aunt," then the number 9. And the same was true for the right ear. Participants were told, as in any dichotic listening task, to attend to only one ear, let's say the left ear in this case. However, participants tended to follow the story that began with "Dear Aunt Jane." In other words, they alternated ears in terms of what they were paying attention to, even though they were directed to only pay attention to one ear. What this suggested was that participants couldn't help but notice that there was a meaningful, coherent message that was alternating between the two ears. This is a challenge to early selection models because, according to those, participants should never have noticed that the unattended ear was providing meaningful words that were coherent with what had been presented with the left ear. In order to respond to these and other challenges, Treisman presented the attenuator model. According to the attenuator model, the filter of attention is not complete. While attended information is processed more fully, unattended information is also processed, just at a reduced rate. Attenuation simply means the reduction or minimization of those particular stimuli. The idea behind the attenuator model is that although we don't fully process unattended information, we process it to the extent that very significant information, like for example our name, or predicted information, such as that in the Dear Aunt Jane experiment, might be interpreted and processed enough that we're able to recognize those stimuli. We could think of this as something like hearing a noisy or staticky sound recording. Even though we might not be able to make out the words well, if something important, like our name, came up, we might just notice, even though the signal is very degraded. Similarly, the low level of processing of unattended stimuli provides something like a degraded stimulus to the brain. If something important is contained within it, the brain might be alerted, even if the signal is not that clear.